Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to start by doing a quick auditory and visual thought experiment with me.
Okay, I'm game.
So imagine you are walking outside tonight. You're somewhere completely isolated, right? Miles and miles away from the light pollution of any major city, and you just look up at the night sky.
And you really have to let your eyes adjust to the darkness for, a good 20 minutes to get the full effect.
Exactly. And under ideal conditions, with perfect vision, in the absolute darkest possible spot on Earth, your naked eye can pick out roughly, I think it's 2.5 to maybe 3,000 individual stars.
Yeah, that sounds about right.
And honestly, just staring into that vault of 3,000 points of light is usually enough to trigger this profound sense of vertigo in anyone who really stops to think about what they're looking at.
It's that crushing, overwhelming realization of cosmic scale.
Right. It's a physical sensation of feeling incredibly, unfathomably small. So I want you to hold on to that exact feeling of awe, and I want you to multiply that feeling by 4 billion.
Which, the human brain simply does not possess the cognitive architecture to visualize 4 billion discrete celestial objects. We can't do it.
No, it's impossible.
We can write the number down, we can run mathematical operations on it, but actually holding the visual reality of 4 billion distinct galaxies and stars in your mind simultaneously is just a biological impossibility.
Okay, well, let's unpack this because we aren't just playing with theoretical math today. Yesterday, August 10th, 2026, this monumental event occurred in the astrophysics community.
A literal paradigm shift.
Yeah. The team behind the DESI Legacy Imaging Surveys officially released the largest, most detailed two-dimensional color map of the universe that humanity has ever assembled.
And we should clarify, this isn't just a loose collection of disparate photographs in a folder somewhere.
Right. No, it is a single, unified, continuously navigable image comprising an unfathomable 5.6 trillion pixels.
The release of this data fundamentally alters our relationship with the cosmos. It really moves astronomy from a discipline of isolated observation into an era of holistic total environment modeling.
Because it's practically everything we can see.
Exactly. This massive map is serving as the foundational blueprint that astrophysicists are currently using to unravel some of the most stubborn mysteries in physics. It is the framework upon which the next century of cosmology will be built.
So the stakes here are, astronomical in every sense of the word. We're going to explore the mechanical and the computational nightmare of how an image of this magnitude was actually engineered in the first place.
Because it is a nightmare.
Oh, completely. And we're also going to look at the hidden structure of dark matter that this map brings into the light. But the real destination of this conversation, and I think the reason this map is dominating every single scientific channel today, is this shocking recent discovery enabled by this very data.
A discovery that might force us to entirely rewrite the ultimate fate of our universe.
Yeah. We're looking at early data indicators that challenge, decades of deeply entrenched foundational cosmological theory.
Yes. The standard models of physics are actively being interrogated right now because of what is hidden in those 5.6 trillion pixels.
But before we reach the actual edge of the universe and, the unraveling of theoretical physics as we know it, we really need to anchor ourselves in the sheer physical scale of this map.
Right. We need to understand what we're looking at first.
Exactly. 5.6 trillion pixels.
Okay.
Let's just try to contextualize that for a second. If you were to display this map on a high-end 4K monitor, which, pushes about 8 million pixels on its own, you would need to stack nearly 700,000 of those monitors edge to edge just to view the entire map at its native uncompressed resolution.
And that's just a staggering physical footprint.
It catalogs nearly 4 billion objects.
Yeah.
And we aren't just talking about local stars here, right?
No, mostly we are looking at entire distant galaxies, each one containing hundreds of billions of their own stars.
But in reading the technical specs of the release yesterday, there's this massive caveat that immediately jumped out at me. This map is being touted as the most comprehensive view of the cosmos ever created, but it only covers roughly 75% of the sky.
Yeah, that limitation is dictated entirely by our physical location in space.
Wait, hold on. If the objective was to map the entire universe, why stop at 75%? What physical barrier is hiding a full quarter of the cosmos from our most advanced telescopes.
Well, to visualize this, think about trying to look out of a heavily smudged, dirty window while someone has a brutally bright halogen lamp turned on right behind you inside the room.
Okay, yeah, I could picture that.
You want to see the distant mountains outside, right? But the glare reflecting off the grime right in front of your face completely blinds you to the landscape.
You literally can't see past the glass.
Exactly. So the dirty window and the blinding lamp represent the structural reality of the Milky Way galaxy. We, as observers, operate from a highly disadvantageous vantage point for extragalactic astronomy.
Because we're stuck inside it.
Right. Our solar system is embedded deep within one of the spiral arms of the Milky Way, roughly halfway out from the galactic center. So when we look out into the broader universe, we have to look through our own galaxy to see it.
And I'm assuming that's the dirty window.
It is. The Milky Way contains hundreds of billions of stars generating immense light, the halogen lamp. But more problematically, the galactic plane is choked with vast clouds of interstellar dust and cold molecular gas.
The grime on the window.
Yes. Interstellar dust is incredibly efficient at scattering and absorbing visible and ultraviolet light. So astronomers historically refer to the plane of the Milky Way as the zone of avoidance.
The zone of avoidance. That sounds like a sci-fi movie title.
It does, but it's a real technical term. For decades, if you pointed a telescope in that direction, the dust extinction was so severe that the distant extragalactic universe was completely rendered invisible. You simply couldn't see past our own local neighborhood.
So let me make sure I have this right. The 75% of the sky mapped in this 5.6 trillion pixel image represents the sightlines where we can look up out of the galactic disk or down out of it, deliberately avoiding the dense, dusty equator of the Milky Way.
Precisely. By pointing our instruments perpendicular to the galactic plane, we bypass the thickest concentrations of dust. The map surveys these specific, clear regions of the sky in both visible and near-infrared light.
Because the goal wasn't to map the Milky Way.
Exactly. The objective of the legacy surveys was never to map our own galaxy. It was to achieve the deepest, most unobstructed view of the extragalactic universe beyond our borders. When you navigate this map, you are essentially looking past the scattered foreground stars of our galaxy and plunging directly into the deep ocean of the ancient universe.
And the landmarks in that deep ocean are they're staggering. I want to paint a mental picture for you listening because the specific galactic structures captured in this map really defy simple description.
They are incredibly beautiful.
One of the highlights the survey team isolated yesterday is Messier 96. It's this massive intermediate spiral galaxy located in the constellation Leo. And the resolution of this 2D map captures it with such terrifying clarity.
You can see the sweeping, highly asymmetrical spiral arms.
Yeah, and the intensely bright, active galactic nucleus in the center, and these intricate, dark tendrils of cosmic dust woven through the outer disk. It's breathtaking. But the detail that gives me absolute pause is the distance. Messier 96 is situated approximately 35 million light-years away from Earth.
And the conceptual leap required to understand that distance is essentially a loop in understanding the physical nature of time itself.
Because it's not instantaneous.
Right. Because light travels at a finite, measurable speed, roughly 186,000 miles per second. Astronomy is fundamentally the study of the past. When you look at Messier 96 in this map, you are not seeing the galaxy as it exists on August 11th, 2026. You are interacting with ancient history.
We are looking at a snapshot taken 35 million years ago. So the photons hitting the telescope sensor physically left that galaxy before human beings even existed.
Think about the physical journey of those photons. 35 million years ago, Earth was in the late Eocene epoch.
The Eocene epoch, wow.
Yeah. The supercontinents had broken apart, but the globe looked vastly different than it does today. Antarctica was just beginning to develop its first permanent ice sheets.
So no ice on Antarctica yet, basically.
Just starting. And the earliest primitive ancestors of modern mammals were just establishing their presence. Now, at that precise geological moment on Earth, deep inside the glowing core of Messier 96, a star underwent nuclear fusion and emitted photons of light.
And those photons just started flying outward.
They escaped the gravitational pull of their host star, they navigated out of the spiral arms of Messier 96, and they entered the freezing, near-perfect vacuum of intergalactic space.
And then they just kept going.
For 35 million years, those individual packets of light traveled across the void completely uninterrupted. They dodged rogue planets, they navigated the gravitational warping of dark matter halos, and survived the immense silent stretches between galaxies.
while, entire species rose and went extinct back here on Earth.
Exactly. And finally, after a 35-million-year, unfathomably lonely journey, they crossed into our solar system, penetrated the Earth's atmosphere, and ended their existence by striking a digital CCD sensor on a telescope in the mountains of Chile.
Triggering a microscopic electrical charge that became a single pixel in this map.
Yes.
When you frame it like that, looking at a galaxy isn't just data collection. It's a literal physical intersection with deep time.
It is.
And Messier 96 is just one object out of 4 billion. The map is crowded with these ancient structures. Take the Copeland septet, which is also featured prominently in the release. It's this tight, chaotic visual cluster of galaxies, again in the constellation Leo.
And in the map, when you look at that cluster, you aren't just seeing static shapes.
No, you are looking at a gravitational war. These massive galaxies are actively dancing with one another. Their immense gravitational fields pulling and stretching each other, tearing off massive tidal tails of stars.
You are viewing a snapshot of structural violence playing out over millions of years.
And the most incredible aspect of this entire endeavor is the accessibility. This isn't classified data locked behind some biometric vault at a defense agency, right?
No, not at all. And the democratization of this massive data set is arguably as significant as the technological achievement itself.
How so?
Well, the astrophysics community has increasingly recognized that hoarding data restricts discovery. The entire 5.6 trillion pixel map is fully public right now, today, integrated into an interface called the Legacy Survey Sky Viewer.
David Schlegel, who's one of the co-leads of the Legacy Surveys out of the Berkeley lab, made a comment yesterday that really stuck with me. He noted that this map is no longer just a project. It has become, quote, part of the fabric of astronomy research.
Which is entirely accurate.
It's basically the foundational operating system for astronomers now. If you are researching extragalactic phenomena today, your very first step is opening the Sky Viewer to establish your coordinates. It functions like a hyper-advanced Google Earth, but built for the observable universe.
The ethos behind this was perfectly articulated by Arjun Day, an astronomer at the NSF NOIR lab and another co-lead on the project. He stated quite simply, "The skies belong to everyone."
The skies belong to everyone. I love that.
The interface is specifically designed so that anyone with an internet connection can interrogate the data.
So this means you, listening to this right now, can literally open your laptop, pull up the Sky Viewer, and actively pan through 35 million years of deep space history. And because there are 4 billion objects in this map, the statistical probability is actually very high that you could zoom into a sector and be the first human being in history to lay eyes on a specific distant galaxy.
That happens quite frequently, actually.
There's a massive active community of citizen scientists using this exact data set to hunt for transient phenomena. They're manually scrubbing through regions looking for fleeting supernovae, those stars that undergo catastrophic collapse and explode, appearing brightly for a brief window before fading.
Or they're hunting for rare gravitational lenses.
Right, where a massive foreground object literally warps the fabric of space-time, bending and magnifying the light of an entirely different galaxy hidden far behind it. You can literally participate in cutting-edge astrophysics from your couch in your living room.
But while the public access is beautifully seamless, the interface heavily masks the brutal complexity of the map's creation. Navigating the data is easy. To understand the engineering challenge here, you really have to discard the notion of a photograph entirely. This map is a composite mathematical construction.
Explain that.
The final image is the culmination of 263,407 individual, highly calibrated telescope exposures.
Over 250,000 separate observations. Let that sink in.
Amassed over 2,285 distinct nights of observation.
Wow.
That represents thousands of nights where operators sat in freezing control rooms on high-altitude mountain peaks, monitoring minute fluctuations in atmospheric pressure and humidity, just waiting for the elusive pockets of perfect visual clarity known as good seeing conditions.
And this wasn't just a single telescope slowly scaling the sky over those 2,285 nights either. The data was stitched together from 3 massive, distinct, ground-based astronomical surveys, right?
Correct. To cover the entire mapped area, you need multiple vantage points on Earth.
So in the southern hemisphere, you had the DECAL survey operating out of Chile. They utilized the Victor M. Blanco 4-meter telescope, which was outfitted with the dark energy camera, which is this 570 megapixel sensor specifically fabricated by the Department of Energy for this exact kind of wide-field mapping.
Right, that handled the southern sky.
Then, to cover the northern sky, they ran the MZLS survey out of the Kitt Peak National Observatory and the base survey at the Stewart Observatory in Arizona. And as if harmonizing 3 different ground-based observatories wasn't complex enough, they integrated years of space-based data from NASA's WISE satellite.
And integrating the WISE satellite data was an absolute necessity for structural mapping.
Why? Why weren't the ground telescopes enough?
Ground-based optical telescopes are phenomenal, but they are inherently limited by the Earth's atmosphere, which actively absorbs and blocks vast portions of the electromagnetic spectrum, particularly infrared light.
Right, the atmosphere acts like a filter.
Furthermore, visible light struggles to penetrate the massive clouds of cosmic dust we discussed earlier.
The dirty window.
Exactly. By layering the space-based infrared data from WISE, the map can reveal the thermal signatures of deeply dust-enshrouded galaxies, active black holes, and ancient, highly redshifted stars that are completely invisible in standard optical wavelengths.
Okay, let's talk about the stitching process, because this is where my mind hits an absolute wall. If I take my smartphone to the edge of the Grand Canyon to shoot a panorama, I slowly pan the camera from left to right.
And we all know how that usually goes.
Right. The internal processor and software desperately try to match the edges of the frames and stitch them together into a wide shot. But if a bird flies through the frame, or my hand shakes even a little bit, the parallax effect completely ruins the image.
Yeah, the software gets confused by the depth.
Exactly, and you end up with a photograph where a mountain looks digitally sheared in half, or the sky is jaggedly pixelated. It's incredibly fragile technology on a phone.
The parallax effect and the limitations of consumer gyroscopes make seamless panoramic photography on Earth notoriously difficult.
So how on earth do you avoid that when your panorama consists of 263,407 photos? And you didn't just pan a single camera from one spot. You took some photos in the Andes Mountains, some in the Arizona desert, and some from a satellite hurtling through a low Earth orbit.
All operating under totally different conditions.
Yes. These exposures were captured years apart. During some observations, the moon was full, flooding the sky with ambient light. During others, it was pitch black. Atmospheric turbulence varied wildly from night to night. How do you align 250,000 desperate exposures into a unified, flat, 5.6 trillion pixel map without creating a distorted, misaligned, funhouse mirror version of the universe?
You cannot rely on physical sensors like gyroscopes to track the camera's position. In modern astrophysics, alignment relies entirely on celestial reference frames and immensely complex algorithms.
Okay, break that down for me.
The fundamental challenge you are highlighting is why modern astronomy has evolved into a highly specialized branch of computer science. We no longer primarily observe the universe, we compute it.
The computational bottleneck. Tell me how the algorithm actually takes a blurry photo from Arizona and a sharp photo from Chile and forces them to agree on the precise location of a star.
So the software must account for something called the point spread function, or PSF.
Point spread function.
Okay. Because of the Earth's atmosphere, a perfectly sharp point of starlight gets smeared and blurred by the time it hits the telescope sensor. This smearing changes every millisecond based on temperature and wind.
The atmosphere is basically constantly boiling above the telescope.
Exactly. So the algorithms written for this map have to mathematically analyze every single star and every single exposure, calculate the exact nature of the atmospheric blurring for that specific microsecond, and then run complex deconvolution matrices to reverse engineer the true sharp position of the light source.
Wait, so the software isn't just overlapping images. It is actively mathematically repairing the atmospheric distortion in millions of stars simultaneously.
Yes, but it goes further than that. The software must also differentiate between a genuine cosmic object and a transient error.
Like what kind of error?
Well, high-altitude sensors are constantly bombarded by cosmic rays. These are high-energy particles that strike the silicon and register as a bright pixel on the image.
Oh, so it looks like a star, but it's just a particle hitting the camera.
Exactly. So the algorithm must compare multiple exposures of the same patch of sky, identify the pixels that only appear in one frame, classify them as cosmic ray strikes or passing satellite streaks, and digitally excise them from the final composite.
That sounds like an insane amount of data processing.
It is. Writing the custom software architecture capable of performing these millions of simultaneous calculations took the development team an entire year.
A full year of just coding the logic before they could even attempt to render the actual map.
And when the code was finally optimized, it required a hardware environment far beyond standard high-performance computing clusters.
You can't just run this on a MacBook.
No. They had to deploy this architecture on the Perlmutter supercomputer, housed at the National Energy Research Scientific Computing Center, or NERSC, at the Berkeley Lab. Perlmutter is explicitly designed for extreme-scale scientific computing.
And even with millions of processing cores operating in parallel, chewing through petabytes of raw observational data, the rendering process was not instantaneous, right?
Far from it.
It took 8 grueling, continuous weeks of supercomputing time just to process the math and synthesize the final 5.6 trillion pixel image. I read that if a standard high-end commercial laptop attempted to run those calculations, it would take centuries of constant processing.
The scale of the computation reflects the scale of the ambition. But, it is crucial to understand that rendering this beautiful 2D map was never the ultimate goal.
It wasn't.
No. The Legacy Imaging Surveys did not commandeer years of supercomputing time just to produce a static visual catalog for people to look at. This 2D image is functionally a stepping stone.
Okay, to what?
It is the highly calibrated foundational blueprint for a 3D structural model of the universe designed to interrogate the most dominant invisible forces in nature.
Oh, wow. Okay, this transitions us perfectly from the map itself to the actual reason the map exists. We need to talk about DSI, because if you want to understand why astrophysicists are currently questioning the long-term fate of the universe, you have to understand the interplay between this newly released 2D map and the dark energy spectroscopic instrument, right?
Exactly. The Legacy Imaging Surveys were commissioned and executed specifically to provide the targeting data for DESI.
To make this concrete for the listener, let's look at the limitations of the 5.6 trillion pixel map. As detailed and as massive as it is ultimately a flat two-dimensional projection.
Right, it has no depth.
It provides exact X and Y celestial coordinates, and it provides precise photometric brightness. But a 2D photograph suffers from a fundamental astronomical ambiguity. It cannot inherently tell you distance.
You lose the z-axis entirely.
Exactly. If I look at the map and see a small, dim smudge of a galaxy, and right next to it I see a massive, bright galaxy, I cannot automatically assume the dim one is physically smaller.
Right. The dim galaxy might be relatively close to Earth, but objectively tiny, while the massive, bright galaxy might be an absolute behemoth located billions of light years further away.
In a flat image, depth is collapsed.
The 2D map is an exquisite, comprehensive catalog of where objects appear in the sky, but it lacks that crucial z-axis. It is essentially the menu from which DESI selects its targets.
So how does DESI extract that z-axis? How does it take this flat map of 4 billion objects and begin assigning them a physical depth in a 3D model?
DESI utilizes the exact coordinates provided by the 2D map to aim its instrument. But DESI doesn't take photographs, it is a spectrograph.
A spectrograph. Okay, how does that work?
It uses thousands of robotic positioners to point microscopic optical fibers at specific targeted galaxies identified in the map. Once locked on, DESI collects the light from that specific galaxy and fractures it into a highly detailed spectrum, basically a rainbow of its constituent wavelengths.
And hidden within that spectrum are the chemical fingerprints of the galaxy.
Specifically, DESI is looking for emission and absorption lines. Because, as we know, the universe is expanding, which means the fabric of space-time itself is stretching.
Right.
As the light from a distant galaxy travels toward Earth, the physical expansion of the universe stretches the wavelength of that light, shifting it toward the red end of the electromagnetic spectrum. This is known as cosmological redshift.
So wait, it is just the Doppler effect, like a police siren changing pitch as it drives past you on the highway?
Not exactly. The galaxy isn't merely moving through space. The space between us and the galaxy is actually expanding, stretching the photon's wave while it's in transit.
Okay, that distinction is vital.
By precisely measuring how far those spectral lines have been shifted toward the red, DESI can calculate exactly how much the universe has expanded since that light was originally emitted.
And because we know the rate of expansion, the redshift measurement gives us an exact, highly precise distance to that galaxy.
Exactly. DESI combines its precise depth measurements with the X and Y coordinates of the 2D map to build a sprawling, immensely detailed, 3D topographic map of the cosmos.
But the ultimate purpose of plotting millions of galaxies in 3D isn't just to know where they are, it's to trace the massive invisible scaffolding that governs their movement. We are hunting dark matter and dark energy here.
The structure of the universe is dictated by a cosmic tug-of-war between these two invisible dominators.
Okay, let's break down the teams in this tug-of-war. Dark matter first.
Dark matter acts as the gravitational glue. It exerts a powerful attractive force. It is the underlying mass that forms the immense cosmic web, pulling regular baryonic matter together to form galaxies and clustering those galaxies into massive superstructures.
So if dark matter were removed, what would happen?
The rotational velocity of galaxies would cause them to instantly fly apart. There isn't enough visible matter to hold them together.
Wow. Okay, so dark matter pulls in. But we know the universe is currently expanding, meaning something else is pushing back, and that something else is winning.
Dark energy is the opposing force. It acts as a repulsive pressure inherent to the vacuum of space itself, driving the accelerated expansion of the universe.
And DESI is measuring this?
Yes. By analyzing the 3D distribution of galaxies over vast cosmic timescales, scientists can study baryon acoustic oscillations.
Baryon acoustic oscillations?
Yeah.
It's a mouthful. What are those?
They're essentially frozen sound waves from the early universe that dictate how galaxies cluster together today. By measuring the exact distances between these clusters at different epochs in the universe's history, we can precisely chart the behavior of dark energy over time.
Which brings us directly to the absolute bombshell discovery that is actively rocking the physics world right now.
Yes, the early DSI results.
DSI was initially utilizing an older, smaller iteration of this 2D map to select its targets, right? And the instrument proved so incredibly efficient at mapping the z-axis that it burned through its initial target list way faster than expected.
It completed its primary 5-year survey ahead of schedule in April of 2026.
They literally ran out of galaxies to measure. They desperately needed the expanded boundaries of this new 5.6 trillion pixel map to continue the hunt, and the DESI team actually began quietly utilizing this new data behind the scenes in June of 2026 to select fresh targets.
The influx of new targets from this expanded map was critical because the initial data crunch from DESI's first years of operation revealed something deeply, deeply unsettling about the nature of dark energy.
Let's clarify why this is so unsettling. For essentially my entire life and for decades of established cosmological theory, dark energy was assumed to be a cosmological constant.
Right, it was a fixed rule of the universe.
When Albert Einstein formulated general relativity, he introduced the cosmological constant, represented by the Greek letter lambda, to basically balance his equations. In the modern consensus model, which is known as lambda CDM, dark energy is a constant, unchanging property of space.
Meaning, as the universe expands and creates more space, the density of dark energy remains exactly the same.
It applies a constant, uniform outward pressure, causing the universe to expand faster and faster into eternity. But the early results from the DSI data are actively defying this model. The clustering of the galaxies suggests that the impact of dark energy is not constant.
It is showing significant hints of weakening over time.
Weakening?
Yes. The implications of dynamic dark energy cannot be overstated. If dark energy is weakening, if its density or its repulsive force changes as the universe ages, then Einstein's cosmological constant is fundamentally incorrect.
That is massive.
We would be forced to abandon the lambda CDM model entirely and adopt entirely new theoretical frameworks, such as quintessence, which posits dark energy as a dynamic, evolving scalar field rather than a static property of the vacuum.
But wait, I need to push back on the actual mechanics of this for a second. If dark energy is the physical pressure causing the expansion of the universe to accelerate, and that pressure is running out of gas and weakening, what happens to the physical expansion?
Well, it changes everything about our future.
If I'm pressing the accelerator on a car and I slowly lift my foot, the car doesn't stop immediately, but the acceleration drops. If dark energy weakens enough, does the expansion of the universe just coast to a halt? Does it reverse?
You are outlining the exact existential scenarios currently being fiercely debated by theoretical physicists right now.
Let's talk about the traditional scenario first.
Under the traditional model, where dark energy remains a constant, relentless force, the fate of the universe is locked into a scenario known as the Big Freeze, or heat death.
The Big Freeze.
The expansion continues, accelerating infinitely. Galaxies drift so far apart that they can no longer be seen from one another. The stars burn through their fuel and die, the remaining matter decays, and the universe becomes an endlessly expanding, dark, freezing void, approaching absolute zero.
An infinitely lonely, frozen eternity. Not a great way to go out.
No, it's quite bleak. However, if the DESI data holds true and dark energy is dynamically weakening, that fate is completely rewritten.
Okay, how so?
If the repulsive force of dark energy diminishes enough over cosmic time, the outward expansion of the universe will inevitably slow down. The critical threshold occurs if dark energy weakens to the point where it is finally overpowered by the collective gravitational pull of the dark matter scaffolding.
The moment gravity wins the tug-of-war.
Exactly. If gravity becomes the dominant force once again, the expansion of the universe stops and it begins to contract. This leads to the big crunch scenario.
Big crunch. So everything comes rushing back together.
Yes. Billions of years from now, galaxies would begin rushing toward each other. The ambient temperature of the universe would violently rise as all matter and radiation are compressed into a smaller and smaller volume, eventually collapsing back into a state of infinite density.
Basically a reversal of the Big Bang.
Precisely.
The fact that this 5.6 trillion pixel map, which was officially released to the public yesterday, is the primary instrument dictating whether our universe freezes into infinite nothingness or collapses into a catastrophic singularity is genuinely difficult to process.
It's heavy, for sure.
And we won't even have to wait decades for an answer. DSI is scheduled to publish a highly refined analysis of its first 5 years of data in 2027, and it will aggressively continue observations using this new 2D map well into 2028.
Yeah.
We are sitting on the precipice of a complete paradigm shift in physics.
The immediacy of these discoveries is thrilling, but the utility of this map extends far beyond just the DSI project.
Really? How much more can we get out of this data?
The Legacy Surveys team has fundamentally constructed an infrastructural asset that will anchor observational astronomy for the next 50 years.
Oh, we are talking about the technological foundation for the next generation of massive observatories.
Exactly.
We are currently building phenomenal multi-billion-dollar machines like the NSF DOE Vera C. Rubin Observatory in Chile and NASA's Nancy Grace Roman Space Telescope. The capabilities of these new instruments are just unprecedented.
They are the absolute pinnacle of human engineering.
But to use an analogy, building these massive telescopes is sort of like engineering a hyper-advanced sniper rifle. It has incredible range and terrifying precision. But if you look through the high-powered scope, your field of view is incredibly narrow.
Right, you can only see a tiny sliver of the sky.
You can see a microscopic patch of the horizon in incredible detail, but you have zero situational awareness. You can't just blindly sweep a sniper scope across the sky hoping to find a specific target. You need a wide-angle drone feed, a highly detailed map of the entire battlefield to tell you the exact coordinates of where to aim the rifle.
And that is exactly what this map provides. The 2D map is that comprehensive wide-angle feed. Because telescope time on the Rubin Observatory or the Roman Space Telescope will be incredibly expensive and highly contested among scientists worldwide, efficiency is paramount.
They can't waste time looking in the wrong place.
They cannot waste hours blindly scanning. When these next-generation observatories achieve first light, their targeting algorithms will pull directly from the 5.6 trillion pixel map to execute their deep field observations.
And it isn't just human astronomers writing grant proposals who will rely on this data. The map is actively training the non-human intelligence that will dictate the future of discovery.
This is a huge shift in the field.
We are crossing the threshold into an era where AI fundamentally drives astrophysics.
Because the volume of data has simply surpassed human biological limits. When you have a unified image containing 4 billion objects, human review is mathematically impossible.
You could have 1 million grad students staring at screens and they wouldn't finish it.
Exactly. This is why the MAPS data has immediately been integrated into a massive astrophysics pilot project within the American Science Cloud, operating under the Department of Energy's Genesis mission.
So the objective isn't to have an AI just, count the galaxies, right? They are feeding this petabyte-scale map into massive neural networks to teach the AI the fundamental visual and structural rules of the universe.
The neural network analyzes the millions of variations of spiral arms, the typical thermal decay of cosmic dust, the standard luminosity gradients of elliptical galaxies.
Basically learning what normal looks like.
By ingesting trillions of pixels of standard cosmic behavior, the AI establishes a rigorous mathematical baseline for what normal physics looks like. And in astronomy, discovery does not come from observing the normal. It comes from isolating the anomalous.
So if a bizarre burst of radiation occurs or a galaxy exhibits a structural deformity that doesn't align with the standard model of gravity, the AI flags it immediately. Instead of a graduate student spending 6 months staring at photographic plates hoping to notice a slight discrepancy, the AI will theoretically scan incoming data feeds, cross-reference them with the 5.6 trillion pixel baseline, and instantly alert a research team to an anomaly in the fabric of space.
We are rapidly transitioning from human-led observation to AI-driven anomaly detection. The algorithms will highlight the fractures in our understanding of physics, and human scientists will investigate those fractures.
It is a radically different landscape for exploration than we had even 10 years ago. If we step back and look at the trajectory of everything we've explored today, the scale is almost overwhelming.
It really is.
We started with the sheer logistical terror of compiling 263,407 atmospheric exposures, utilizing a year of custom coding and 8 weeks of supercomputer processing to render a 5.6 trillion pixel image.
Just a monumental effort.
And then we transitioned from that 2D map into a 3D hunt for the invisible scaffolding of dark matter. We navigated the stunning, deeply unsettling early data, suggesting that the force pushing our universe apart is actively weakening, threatening a total cosmic collapse.
The big crunch.
Right. And finally, we look at how this massive public map is currently training the AI that will run the next generation of massive observatories.
But I think the defining characteristic of this achievement is that the map is not a closed system.
What do you mean?
The entire 5.6 trillion pixel catalog of the universe is sitting on open servers right now. The barrier to entry for cosmic exploration has been completely dissolved.
Anyone can access it. Which leaves me with a final lingering thought for you listening. I want you to genuinely consider this the next time you step outside and look up at the dark sky. We know that the early targeting data pulled from this map has already provided the initial hints that dark energy is weakening, a revelation that could entirely break the standard model of cosmology.
The biggest discovery in decades.
Yeah. If that paradigm-shifting discovery was unearthed just in the initial passes of the data, what completely unimaginable alien forces are currently hiding inside those 5.6 trillion pixels?
It's just waiting to be found.
The architecture of new physics is sitting on a public server right now, silently waiting for a future AI, or perhaps a deeply curious citizen scientist panning to the sky viewer on a quiet Tuesday evening to finally notice it. Thank you so much for joining us on this journey today. Keep looking up.